Hello everybody, welcome. This episode is about type system. Type system is the engine that gives you errors and warnings in code telling you that something is wrong. For example, here it's telling us that we can't assign string into an integer variable, obviously. So we're violating some sort of constraint, a type system rule that is defined in that language, and then declares that the initializer must be of the same type as the type of the variable. Each time you see such an error, you can always click on it and go to the rule definition, and now you see which rule causes the trouble. And also this is an example of an inference rule, a rule that you can define in type system, a rule that declares that certain parts of the code should have certain type, or that types of these two parts should be in some relation. In our case, we're creating a relationship that indicates that the type of the initializer must be equal or subtype of the variable declaration. Notice there are several options here. Either subtyping, equation, or subtyping going the other way around, or compatibility between the two types. So you pick the relationship between the two types, you use the type of operator to indicate you are now doing calculation on the future calculated type of the node that you put in the parentheses. And you might pick between inference rule, so this rule will enter the calculation and will become part of the rule set that the rule engine uses for type system calculation. Or you might set the check only flag to true. In that case, this rule will not be part of the calculation. It will only be checked afterwards that it holds, after the types are calculated. So this is the essence. You combine base language with the type system specific language to create various types of type system rules. These type system rules are organized into the type system aspect of language definition. And here you might create the type system rules. There are several options, and we'll go through some of them during this short tutorial. Now these rules enter some computation, and that computation will give out the results in the form of highlighting in the code. In red you see errors, in yellow you see warnings. Or you might also check models for errors. If you go to a model or a module and you right-click on it, and you pick the check model or check module or check language option, it will run the type system checks on the selected model or module and report all errors and warnings it finds in there. So it found the error that we introduced here. So you don't have to open a file just to find an error in there. And by default, these checks are also part of the code generation process, but you can turn it on and off in the settings to indicate whether the models and modules should be checked before the code generation starts. Let me give you a concrete example here. A custom extension to Java called the decision table that allows you to create this sort of construct, which is a table that evaluates conditions in column and row headers, and those that are true are then used to indicate the value that should be returned from the table. The value is not a plain value, it can be an expression of any type, or you could call methods from here, or reference to variables, whatever you like. But ultimately, the whole table returns a value of some type, and you can use that value to, for example, assign it to a variable. And the table itself declares the type of itself. So if we change type to int, now it will report a problem that we declare the table should return an int, but we're here providing a string value. And also we're assigning to a string variable. So this is probably not quite right. Or the other way around, if we declare this a string and we return a float value from here, we again get an error that, well, double is not a subtype of string. So the creator of this decision table had to provide rules for the type system so that the type system could check the types. And here is how it was done. So for this decision table, now first we should probably look at the structure. So a decision table has an expected type. So this is this word here where we say which type we expect back. Now a default value that holds if none of the conditions is true. So this is this value here. And then it has the headers for columns, headers for rows, which are all expressions, and then the result values that are the values in the cells. And all of them are expressions. First, the type system declares that the expected type that you explicitly declare is the type of the whole decision table, so that the assignment, for example, can be evaluated by the type system, because this is a local variable declaration, and the local variable declaration indicates that the type of the initializer must be a subtype of the variable declaration. So if there wasn't a match, then we would get a type system error telling us that double is not a subtype of string. Now, if we, for example, were expecting an integer, now we would get an error telling us that string, the type of the whole decision table, is not compatible with the type of the variable. Now we would get an error because of this type system rule. We can easily check that again by right-clicking and going to the rule. Here's the place. This is the place where we get the error. Now, well, if we continue analyzing this type system rule, now what we say here, we iterate through all the row headers and insert a check. So this is only a check. This will not enter the overall type calculation. This will, because this is an inference rule. This is not check only, but these are check only. The word check here also indicates this is a check only rule. So we add a couple of checks that after the computation is done, that will verify that all the headers and for columns and rows are of Boolean type, because after all they have to say true or false whether that branch or column should be used for retrieving the value, and then also that all the values inside the decision table are of the same type or a subtype of the type of the whole decision table, so they could be used as the result value of the decision table. And we also check the default value that it meets these criteria. And that's it. You can also access the calculated type programmatically. So if you are manipulating nodes, you can always pick a node, this for example, and ask for the type, provided you have the right language imported. So you can get the calculated type and compare it with whatever. So with whatever other type or with your expectation, and use that information somehow in code. Once we are at it, for example, you can use constructs like is subtype, where you specify a type, or let's say two types, and you get a Boolean value telling you whether one is a subtype of the other. Or you may use coercion, where you check whether a certain node with a certain type has a supertype that meets your criteria. For example, we might check if the current decision table's type is let's say integer type, or we could use a pattern and we would specify a more complex condition using the pattern language on the type. For example, whether it is a classifier type for list of integers. A few more examples of type system rules. Let's start from the simplest one, string literal. So here we indicate that a type of a string literal, so if you somewhere type string, Now the type of this is equal to string. Now notice this thing here, this is called quotation, the construction here. Now we are trying to compare the type of string literal to something. That something should be a string type, and this is the easiest way to type a string type. Alternatively, we could create a new node, string type, and we would have an equivalent piece of code. Right, but if you want to build an AST and don't want to spend too much time doing it, now using quotations is faster, especially if you were trying to create, let's say, an if statement with a condition and a true branch and false branch. Now doing it through creating nodes and then setting references properly would take quite some time. So it's always worth considering using a quotation, which is this option. Now you get an isolated workspace in which you create a part of an AST that will then be inserted into here. So we could create an if statement, for example, with some condition and some body. And this would return a node representing such an if statement, including the nested condition and the body here. So this would be much simpler than doing it through the nodes API. Well, in our case here, we only want a string literal, we only want a string type, the node for the string type, and so we wrap it in a quotation, and now it's compared to the input type of string literal, and we've got a rule. Parenthesized expression. So if you've got something in parentheses, you want the type of this to be equal to the type of whatever is inside the parentheses. So a very simple rule like this will ensure that in expressions where you use parentheses, the type is propagated correctly. Now a little bit more involved code for array access. If you've got an array and you access it somewhere, the type of this operation should be the type of the elements of the array. So int in our case, so we can't say this should be string. Now we would get a type system error here telling us int is not a subtype of string. So the rule that says that the type of this is int is this one. So the type of array access is defined this way. Notice we declare a special type system variable here because it will simplify our life in defining this rule. So we create a variable that's valid inside this rule, and we bind this variable. We bind it in this rule. In this particular equation, we bind it. We indicate that the type of the whole array is a subtype of an array of t's. Now the construct here is called anti-quotation. So it's like the opposite of quotation if you want to refer to something from this context from within quotation. So here's a quotation so that we can easily create AST, but from that AST we want to refer back to the host code here. So we use anti-quotation to temporarily subsede the quotation and be able to refer to something in the surrounding code. So this rule says that the type of the whole array should be a subtype of an array of t's. So now this variable is bound by this rule. Then we use t again in another rule where we say that t should be equal to the type of the array access. So the type of the whole array access is t, and we know t is the element type of the array thanks to this equation. So that should guarantee that we get back integer in here. Well, we also indicate that the index in array access should be integer, but that's obvious. So far, we've been looking at inference rules. So rules which insert equations or inequations into the type system rule engine, and also may add a few checks to validate the expected type of certain nodes. But there are other types that can be used as well. For example, there are subtyping rules, rules in which you indicate that a type is a subtype of another type. For example, int is as subtype of a long, because it specializes the values of long, and you can assign integer variables into integer values into long variables. So this is a subtyping rule, and you see there are several options of the types of rules you may create. So we've been looking at inference rules. Now we're looking at a subtyping rule, and then we look at the others as well. In the subtyping rule, we declare which types are the supertypes of the current type. So in our case, it's just long, and that's enough. Now long itself has 3 subtyping rules specifying that long extends float, long extends integral type, and big integer. And these rules look pretty much similar to the ones we've seen for int. But there might be more complex subtyping rules, like the one for linked list, where we return a collection of types, which all can be supertypes of a linked list. So we return a list, deck, and a stack, and the elements for these are supplied through anti-quotations. So here again you see anti-quotations inside quotations, where we refer to the element type of the current linked list to be the element type of the collections that are our subtypes. Then replacement rules. For example, to specify covariance for sequences in base language. If we've got 2 sequences, one called as left, one called as right, and now the now the type system engine is trying to verify a rule that the one on the left is a subtype of the one on the right. So this replacement rule allows the type system engine to remove the rule that indicates the relationship, and instead insert a rule or set of rules that would in our case indicate that the element type of the left collection is a subtype of the element type of the right collection, or sequence in our case. So that's replacement rule. Then comparison rules. You might also indicate to the type system engine that certain types are comparable. They can be used where the other one is expected and the other way around. For example, base language provides its own map type, which looks like this, with a map with small m. While in Java and also in base language, we've got the map class or map interface from the Java util package. So here we indicated these 2 types, the map type from base language and the Java's map, that these 2 types are comparable and can be used where the other one is expected. And we'll look at the last type of type system rules in the context of our robot language. Notice if I duplicate a command like step, the second instance gets underlined in yellow and reports a warning that we should consider using a repeat statements to avoid duplication, to avoid repetition here. And if I hit Alt-Enter on the underlined node, I get a short menu with quick fixes or intentions I can apply. One of them is replace with the repeat command. I hit repeat command, and now the duplication is removed and the repeat statement is inserted. Now this is a job, reporting problems like this is a job for non-type system rules or check-in rules. So this is the 4th type of rules. So we can go to the definition of this one. And here it is. So it is, to put it in context, it is a check-in rule in the type system aspect of the robot Kaya language. It is a check-in rule. So you create this one as non-type system rule. So this would create this node. Just like for all other rules, we specify for which concept it is applicable and whether it should be just added to the list of rules to evaluate, or whether it overrides the one defined on a predecessor of abstract command, and so that the one for abstract command for the predecessor of abstract command should be removed when evaluating abstract command and its subconcepts. Well, and the check-in rule simply checks that we have a repetition of commands that should not be repeated. If the command is one of the concepts and the concept is the same as the one of the next sibling, so the next command in the body, and in case if it's a routine call, then we check it's calling the same method, so we are calling the same routine twice. Then we insert a warning. So this is the way to say to the user, hey, this is wrong here. And optionally, down in the inspector, for each warning, there are more options, not only warning, but you could also just add an info, or you could do an error as well. Right, and for each, you then specify down here certain things. Well, one of the important ones for quick fixes is the intention to fix an error. So here you provide an intention that should be provided, or set of intentions that should be provided in the Alt-Enter menu to the user to fix the problem. You may leave it empty if there's no quick fix, obviously, but you might provide hints, you might provide quick fixes, you might also specify to apply them immediately if the problem is discovered. So you're not waiting for the user input, but typically you want to wait for the user input. Here you specify the quick fix, you might give it some parameters if it expected some. Now let's go to definition of this remove repetition quick fix. So it's a quick fix, it's defined in the type system as well, and you create it through the new menu quick fix. So this one would create it. And in the quick fix, you specify which arguments you take, so you're gonna get all the context you need for your quick fix. You give a description to show in the menu. So this string to show to the user. And then the code that if the user selects the option, so the code that should be executed. In our case, we replace the node with a repeat statement, and we create into the body we add the command, and we set count for 2, and we also delete the other sibling, and that's it. Okay, that's all that we needed to cover. Thanks for watching. Goodbye.